Hey, so welcome back. Last time we left off roughly here, if you can see that at all, yeah, roughly here, where we already covered essentially the main part of Zhang's argument, consists of defining these two functions. This is following the reference given here. And then eventually our goal will now be to show that this inequality holds, and that this will imply the thing about immiscible sets, which then implies bounded gaps between primes. So turns out you evaluate, you make this choice for lambda of n, you do a bunch of very complicated algebra, you end up with this, and you evaluate these terms in terms of this is a linear term, which you probably can't see, and there's two O of whatever terms. And so you want this to be positive for a sufficiently large x, which means that this coefficient in front of the linear term has to be positive, has to be at least as big as this, so that this O of whatever term doesn't kill it being too negative. And then you also have to bound this error term by something reasonably small. So this also doesn't become too negative and then kill the positivity of this term. And that's essentially where we left off. And turns out that you can show that this initial coefficient is positive, or it's positive enough, so it's bigger than L to the 2k or whatever. And this is bigger than the coefficient here, which means that this linear term will be positive and dominate this second term, which is what you want. And you can show this if you choose a constant d, which bounds some of the stuff in these definitions, to be x to the 1/4 plus a small amount. And then the issue with this is the error e or error epsilon can only be bounded in this case if the primes have level of distribution 1/2 plus epsilon. But Bombero Vinograda, which I covered in the last episode or last series, gives it the level of distribution 1/2. So this we don't know is true. And so we can't bound the error. And it turns out I watched some more talks by Zhang, where this is actually the route that he went. He managed to bound this error E without using this assumption, essentially. And then you get this for free just by choosing this. This is a previously known result, but his main contribution is bounding this error. There's kind of another sneaky way you can go about this too, which is Bombero Vinograda is good enough for bounding the error if d is like x to the 1/4 minus epsilon, but then it turns out that even the most general form of lambda you can come up with in this case will not, is incompatible with this growth bound on this first linear term that you want. And you could think about maybe having this be L to the k naught plus 2 L naught plus times log of something, but so it's not quite this fast, but then there's kind of less room to maneuver around there, and so it's not surprising he went this route. And so this is the main contribution of this paper, and this is what we're going to try to understand today. Or not today, sometime. Anyway, with that being said, let's just dive right in. So first observation is that in these sums, T1 star and T2 star, and by T1, so he means the stuff in these two coefficients here, contributions from the terms with defying a large prime divisor are relatively small. Why is this? Compose the constraint, so 2.4. Here's 2.4, it's just where they make this choice of lambda. And this is, I think, motivated by the reference at 7. If I remember correctly, this is the GPY sieve, something like that, in this form. And so here's d dividing p of n. So when we impose the constraint d divides p, where p is the product of the primes, less than the small power of x. Okay, I need to unpack what this first paragraph is saying. Sums 2, okay, the contributions, this, I don't think he's ever said what the sums T1 and T2 star actually are. Might have to work this out to actually understand what's going on, but I'll just accept that the contributions in terms of having a large prime divisor are relatively small. Okay, sure. This, you can post this constraint, p is the product of the primes less than a small power of x. Product of the primes less than x to the 1/4, let's say, which I think is roughly where he wants to do this. Compose the constraint d divides p. So this is what he's talking about when he says that d is less than a small power of x, because here it's d is less than or equal to d, where d is roughly as x to the 1/4 plus or minus epsilon. I think he's taking as the case of this whole paper. So then, don't know if you can actually read this anymore, but we're imposing the restraint d divides p of n, where p of n is this, and this is the product of all of this stuff. Impose the constraint where p is the product of the primes less than a small power of x. Why is this product of primes? Isn't this maybe this is part of his notation that he said before. No, it's actually not. So I should figure out what this like curly p means. Where p is the product of the primes less than a small power of x. Ah, wait. So I think what he's saying here is this is like the start of his contributions. And so all of this stuff before was summarizing the previous work. So his main contribution is, so he's thinking about applying this additional constraint. And so this is like one step towards achieving this bound on the error based on the previous work. So, okay, so this is like a new definition. P is the product of the primes less than a small power of x. And the resulting main term is still greater than this with d given by 2.5. Where's equation 2.5? This is 2.5. Yeah, okay, so throughout this paper, he's going to go down this route. He's going to assume that d is x to the 1/4 plus a small quantity. I don't know why he uses var pi here, but yeah, sure, go ahead. This might be because it's a constant. I think somewhere he mentioned that like he took it to be like 1/1168 or something like that, which is like just barely good enough for it to work. So he's imposing this new constraint in this sum here. So if you can't read that, I'll just write it down again. But this sum here is subject to the constraints. D divides P of n. D is less than or equal to D, which we're going to always take asymptotic to, or like on the equal to 1/4 plus var pi, I guess. And then he's going to bound the error term with that. And he's thinking about imposing an additional constraint. D divides curly p, where curly p is defined as the product of primes less than what? Less than a small power of x. I don't know if he means d in particular. He just says less than a small power of x, but sure, and then p prime. Okay, so he's planning on doing this, which is interesting. The resulting main term is still greater than this. So he manages to maintain this bound. Okay, so he's making this small modification here. So in some sense, the original result, the original choice of lambda was not optimal in the sense that you can apply an additional constraint here, which he did, where you require, so this is kind of restricting the sum more. And so as a result, this lambda is kind of smaller. You're doing a smaller sum. But even then, he still manages to make it sufficiently positive, or actually it's not clear that this would either be better or worse, but apparently he does manage to prove that this main term, this coefficient here that you want to be positive, still goes sufficiently fast. So this condition is still maintained, even if you add the additional restriction here when you're defining lambda, that d divides this new curly p. Okay, so I understand this paragraph. Okay, yep, that's good. Okay, and then what's his second observation? Second observation, which is the most novel part of the proof. Yeah, so this is his first observation, which is apparently not too important or not too surprising, but this is the most novel part, is that with capital D given by 2.5, so D equal to x to the 1/4 plus this var pi, which is going to be small, with the constraint, yeah, okay, and then the resulting error can be efficiently bounded. So this is his main contribution, where he, before using the existing choice of lambda over here, which has already been studied, they're able to get this nice bound on the linear term, but they can't bound the error. And it turns out, what he's saying is if you add that additional constraint here, then you still are able to maintain this nice bound on the linear term, but you can bound the error. And so that's what he's talking about here, and this is the error term, well, the new error term after you make that change to lambda. And this, he finds a way to efficiently bound. If you compare this expression for the error with the expression for the original error up here, they're pretty much the same, well, they're very similar. Yeah, except this one is missing the, this sum is over d divides curly p, and it's missing a Mobius. D divides, oh, well, actually, the Mobius doesn't matter because this is d dividing, and p is a product of distinct primes, so of course there's not going to be no repeated factors, so this Mobius is kind of redundant. So these two error terms are completely identical, except that this one has a sum over, a restricted sum D divides the product of the primes less than small power of x. I'm not sure exactly what he means by the small power of x yet. Is it D? I'm not sure. Presumably talk about this later. Okay, cool. So of course I'm not gonna verify this, but it seems like just a small modification, and then you do the algebra, and then correspondingly you get the small modification out for the error. So that seems plausible. This can be efficiently bounded. This is originally due to the simple fact that if D divides this small product of distinct primes, and D is not too small, okay, so say D is greater than this, sure. Here if D is less than D squared and D is 1/4, D is x to the 1/4 plus var pi. So the fact that he's, since saying not too small, this is kind of a pretty tight bound actually, because this is then D. Yeah, so D is greater than x to the 1/2 minus epsilon, but then if it's going up to only capital D squared, then it's going to be less than D to the 1/2 plus 2 var pi. So it's actually fairly narrow range here, which is weird. But then D can be factored as this with the range for R flexibly chosen. Okay, what is Q? Can be factored as, okay, I guess it's just factored into two terms where you can have a selection of R and then you don't really care about Q. But you can choose R quite flexibly. Okay, sure. See level 4, we will make a note of that. This, roughly speaking, characteristic function of this set may be treated as a well-factorable function, and the factorization is crucial for bounding the error terms. Okay, so this apparently is where his novel contribution is, and this is why this error term will work, whereas the previous one didn't. What is the set exactly? So D squared, so in all of this, we're going to be choosing D is x to the 1/4 plus var pi, and so D squared is essentially x to the 1/2 plus 2 var pi. And so it's kind of a tight bound here. So D between x to the 1/2 minus epsilon, D, and remember this epsilon is arbitrarily small. This is x to the 1/2 plus 2 var pi, where var pi I'm assuming is fixed at small. And then we also have this restriction, and this is a well-factorable function. So this is just rephrasing what he said here, that if D divides curly p, D is larger than this, and then D is less than capital T squared, then you can have kind of a nice factorization where you have quite a bit of flexibility in R. And so this is, I guess this is the technical term for this is a well-factorable function. The characteristic function of this set, yeah, is a well-factorable function. Okay, I should probably look up exactly what the definition of well-factorable is, but it seems like a reasonable definition so far. So we will go with that. Okay, and this is where you choose like var pi equals 1/1068, which I mentioned before. Okay, so it suffices to prove theorem 1 with this, which I already mentioned, and which is henceforth assumed. Okay, and then D is in 2.5, so this just means D is equal to x to the 1/4 plus 1/1168, essentially. And this is going to be true for the remainder of the proof. Okay, and then he chooses var pi to be equal to this. Okay, so yeah, so we get some more information. So my hunch was correct last time, where he is going to essentially assume this form with a specific value for var pi. He's going to make a small modification to this lambda function, where he's going to just add one additional constraint to the sum. It's going to show that this still holds with that constraint added, and then he's going to be able to bound this error term using this observation, which he's presumably going to prove in level 4. So we have a nice outline of where this proof is going to go. Okay, so let g of y be given by this. This looks very similar to... Yeah, this was the original form of the lambda function, which was used before in the original, in previous work, and it looks like 1 over k plus blah, 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 blah. And so this looks extremely similar. There is no sum here, so you can essentially kind of write lambda of n to be what? To be the sum of d divides p of n, d less than or equal to d of, is this correct? Could you just push that in directly? Mobius of d times g of d. If I'm not mistaken, this is, you can just write, just solely comparing this form over here to what this form looks like. Let me just quickly check. Yeah, that seems reasonable. So yeah, okay, so then it looks like this is kind of not quite a Mobius inversion, yeah, not really, but something of this form. So, and presumably, like all his modification here is just going to be stick a d divides curly p into this sum restriction. Okay, G of y equals 0 as y is greater than or equal to d. Okay, sure. And this y is less than d. Okay, y is greater than or equal to. Okay, so in that case, you'd actually, that kind of take care of this restriction already. So you could just express this as an unrestricted sum, because the g of y will take care of this based on this piecewise definition. So this is for the simplification, where L naught is equal to 180. So okay, we choose, we've already chosen K naught to be 3.5 million. We choose L naught, we lose this restriction here, we use this freedom. I have no idea why he chose 180. I'm presuming he's going to explain that later. But yeah, so we have this nice form now where lambda of n is equal to just solely the sum, d divides p of n of Mobius d, g of d. And you can see that, g of d, where p of n was defined here. And this is solely just a function of the admissible set, and then you just shift it and take the product. Right. Okay, cool. Right, d1 is equal to x to the omega for x to the power pi, where this is like 1 over 1.168. P is, okay, this is where he defines curly p, and then d, so this is what he was talking about before, where p is the product of the primes less than a small power of x. So here's where he actually quantifies what small power of x means. So small power means x to the power pi, like 1 over 1.168, and then p, curly p, is defined as just the product of all primes less than that. So this, of course, is a function of x. Yep. Okay, and then this is, what is curly L? Exponent, so we know what 1 over k naught is. This is like a really tiny number. It's like 1 over 3.5 million. And then, where does this curly L come from? Should really figure out a way to better organize these notes. But is this in the... Oh yeah, okay. Should have made a note of this. Curly L is just notation for log x. Sure. Okay, so this is x of log x to a very tiny power. So this is a very slowly growing function, I think, but also it's like an exponential. So I'm not quite sure. Although it's definitely sublinear because x above log is, of course, so of course x above log is linear. So the fact that you're raising this to like a tiny power means it's like very, very sublinear. So this is extremely slowly growing, and this is the same thing, but less bounded by this instead of bounded by x to the over 1.168 or whatever. So I think I should probably check this again, but it looks like this is going to be like much smaller than that. In case this is clearly going to divide this, I think, if it is smaller, because they're both products of all primes less than something. So yeah, okay, sure. I'll accept these definitions. The case that d divides curly p and d is not too small. The factor q in that nice factorization that we had before, right here. We can now have freedom to choose r. May be chosen such that it's co-prime to p naught. Okay. And of course, this is a product of primes, so co-prime just means that it is not divisible by any prime. So basically, the primes dividing q are disjoint from these. So you want this to be kind of the opposite of a smooth number. So you want it to not have any prime factors that are too small. This will considerably simplify the argument. Okay, is this obvious? Is this a statement that we should be able to see now? So in case that d divides this big product of primes, and it's not too small, the factor q in 2.8 may be chosen such that this... Well, I'm not quite sure what he means by may, because I don't know how much freedom we have in choosing r beforehand. So I don't know like how much freedom we lose in r if we do that, but... well, if d divides big product of primes... Okay, so... This is just a product of distinct primes, so that means that d has a bunch of distinct prime factors, and they're all less than d1. That's all this is saying. And so if it divides that and it's not too small, then you can factor it. Okay, yeah, this does make sense. So big P is just a bunch of primes multiplied together. And when you say that d divides curly p, then you're just saying that you just pick some of these primes, multiply them together, and then you get d. And then so p naught is kind of the product of a subset of these primes. So if it's not too small, presumably you have some primes up here, and then you can choose q to be like some subset of these primes, and then this condition will automatically be satisfied. Yeah, so you can have freedom kind of to choose these however you wish q. So as long as no factors here are part of q, so basically d is going to have some prime factors in here, none of them go into q, this thing is automatically satisfied. So this makes sense. If it's not too small, then yeah, sure, I agree. Even if it is too small, I guess you can just choose 1 here and then not have any primes here at all, but I guess that isn't helpful. I'll see exactly how this is used later. Okay, yeah, this will simplify the argument, sure. We choose this to be, yeah, so this is the way I was writing it before. The original choice of lambda from previous work was just d dividing this product of the admissible set of like kind of Mobius-ish version, Mobius times g. But here he is just making a slight modification where instead of dividing d dividing p of n, it's dividing the greatest common factor of p of n and p. And so this is of course equivalent to d divides p of n and d divides curly p. So he's essentially just adding one condition, which is that d must also divide curly p. And this is exactly what he was saying before, where if you just add this one condition and then define the lambda this new way, he's going to show that this will satisfy the nice bound on the main term, as well as be able to bound the error term using this slight modification. Okay, sure. Proof of theorem 1. Main terms are not too difficult to handle. Okay, so since we deal with fixed h, main terms, so main terms apparently are not going to be too much of a hassle. So this is quite different from various sets, blah, 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 blah. Okay, various sets are like 1.2. I should check what 1.2 is. Okay, by 1.2 it just means that almost bound on the gaps of the primes with this modulated by a slowly growing function. So apparently the fact that he fixed h one time because all he wants is prime gaps makes like he needs to do a lot less finagling to actually get the bound on the main term, get that bound on the coefficient, which something t1 star and something t2 star. I should actually remember what that is actually. It's k naught t2 star minus l, where l is again log x. T2 minus, handwriting's horrible, k0 t2 star minus log x t1 star. This is the term he wants to bound, and apparently he's not going to have too much of an issue doing that. Okay, sure. Sounds good. The Cauchy's inequality, the error 2.7 is officially bounded by the following. 2.7 is, okay, so by 2.7 he means the error term. So the error epsilon, or error e, is bounded by this formula for blah blah blah. We have this. Proof of theorem 2 is described as follows. Okay, so this is the first kind of main actual proof in this paper so far. For 1, 2, so, okay, so for I between this and like 3.5 million, we have this. Okay, what does this say? So remember, what is this delta function? And why do we care? Okay, so first, this term here is pretty much what is inside like the inner sum in this error term that he wants to bound. This is with the modification to lambda. And so it makes sense that you want to bound this. And if you're summing over d less than d squared, okay, so it's essentially just this sum. So the error term is this sum from 1 to k naught. If you omit the sum, just look at the individual terms and then kind of ignore these taus, you get exactly the sum, which is bounded by theorem 2. So it makes sense that this would help you bound the error term. I'm not quite sure how he's going to get around the fact that he's ignoring these error terms. I guess they're not going to be too important. At the very least, these are... Yeah, I'm not quite sure. I guess he could like bound these separately and then somehow combine these. It'll be interesting to see what happens later. But this seems like a reasonable first step to bound this error, so that makes sense. With that being said, I should actually understand what these terms are. I think I went over this last time, but I've already forgotten. What is the C of I? Okay, C I of D is this set which is defined in some way, which I guess is useful later, where it's just the residue, essentially like representatives from the residue classes, which are coprimes, so there's at most like phi of D of these. Actually, that's good to note. The size of this cardinality of the set is at most phi of D, which is just elementary, but like it's good to keep track of when you're doing this. And there's an additional restriction, so it's where it's product of this, so D divides the product of C minus hi. Okay. I have no intuition for why this works, but presumably like during the proof we'll get a more clear idea of what exactly the set is for. And so you're just doing that. And so, yeah, so presumably this is going to be looking at something like stuff that is C mod D. What is this delta? I will find out soon. Okay, this delta was this crazy function that was defined here, which of course has a lot of like C mod D in it, so that does make sense. Okay, sure. So this, at least the definitions of these functions seem pretty unmotivated. I guess this is just what happens to pop out if you put the lambda in and then try to find the error term. So it doesn't. It makes sense that like there's no reason why this should be nice. It's not like it was actually constructed to do something, so this just happens to be part of what pops out when you have the error term. So, okay, sure, these things are very complicated, sure. And then the sum is just what was in the sum of the error. Okay. This seems not too motivated besides the fact that it happens to be an error term. But it's good enough for now, and we'll go with that. And it's bounded, it's much less than, presumably it's going to make this precise, x times, like, this is x over log to the power of a of x. And this is interesting because if you remember from the last episode where I talked about Bombero-Vinogradov, like a lot of the bounds on the prime number theorem looks kind of like this. So log to the power of a of x. This is precisely the kind of bound that you would get if you look at the prime counting function minus the logarithmic integral of x. Or with logarithmic, this is just 2x, 2 to x of dt, 1 over log t. And so this is kind of the strengthened version of the normal prime number theorem. Shouldn't repeat myself too much from last episode, but normal prime number theorem says pi of x is asymptotic to this, but actually with quite a large error term. And so this is a much better approximation. It's kind of second order in 1 over log x. And the error term deviation of prime counting function from this is much better. It's x over log to the a of x, where a is any positive number. And if you remember from the notation, a is just a very, like, an arbitrary large positive integer. Okay, so he's going to basically show that this part of the error term is very nicely bounded. And that's theorem 2. So what's the proof of this? We will see. Proof of theorem 2 is described as follows. Combinatorial arguments will reduce the proof to estimating the sum of whatever this is with certain dirichlet convolutions. Okay, so here we're looking at thing over theta functions, where theta is what? Theta is like log n times the characteristic function of the primes. Okay, and so he's first going to kind of do a general bound on this with Dirichlet convolutions, and then there are 3 types of convolutions in the argument. Okay, sure. This is like kind of fleshing out the details of that. So right, x1 is x to the 3/8 plus small number, and x2 is x to the 1/2 minus small number. And I guess these coefficients are the kind of stuff that you go through the proof and then like fill in after you actually figure out what you need. Okay, sure. But essentially, this is roughly square rooted. This is like roughly 3/8. First 2 types, function gammas of the form Dirichlet convolution of alpha and beta such that the following hold. Okay, these conditions look somewhat unmotivated at first glance. So yeah, both of these are of course integer sequences. They're supported on these bounds, these intervals. I have no idea where these capital M's and capital N's come from. What is capital M? I have no idea. It's much less than... Okay, sure. So it seems to be sufficiently small in the sense that it's supported on this. Okay, you can have, I guess, one for each J1. This is, again, the divisor function, so this is just the sum of d dividing m of d to the J1, if I recall correctly, and then times log x. So this is kind of bounded by this divisor function times the log. This, I guess, is kind of what happens in analytic number theory. You get these weird bounds. Sure, okay. They're compactly supported on this nice interval, sure, and they're like bounded above by some like slowly-ish growing function, sure. And this is the same thing, but with some bounds on n, I guess. And then you take a convolution of these, and then you manage to prove a bound on this. Okay, sure. Why is this useful? Is theta actually of this type? Is it of like this particular form? I guess we will find out soon. If it is, this makes sense. If not, I guess he's going to have to do quite a bit more work to actually get this bound effective on theta, which is what he wants. And it also seems strange that if he does this, that he would only be able to state this theorem in terms of like a sum. So I don't think actually that theta is going to be explicitly of this form, because otherwise he would have phrased this in terms of just the term itself and not have to resort to like the average behavior over a sum of stuff. But we will find out soon, I guess. for any Q, R, and A satisfying, like so, A coprime to R following Siegel offset assumption is satisfied. I have no idea why he calls it this, but presumably like, this is a common technique. I should look this up as well. Okay, cool. There is some sort of assumption that he's making here. This does look a lot like, where was it? The definition of the delta function that he defined. Well, he is going to prove stuff about the delta function, so it does make sense that it looks like the delta function. Yeah, here's where he defines the delta function. It's the sum of, I'll just compare it to here. Yeah, so the delta of gamma d comma c is sum of n similar to x and congruent to c mod d. And so here he has n congruent to a of a mod r. So I guess it's basically the same but with different notation, a and r. And of course here you assume c is coprime to d as well. So this looks roughly the same. And then n coprime to q. Okay, that's a new condition that wasn't here, I think. So yeah, so, and then this was what, gamma of n, so here you have beta of n. So this looks very similar to delta of beta r a. It's not quite the same. There's this extra condition here. This part is the same. This part, and also it's missing the n similar to x, I think, part that would be in this. So it's not quite the same. It's kind of similar. N is coprime to qr. So whereas before we had n coprime to d in this second term, where d has been replaced by r. So this is kind of, if q is equal to 1, then I think this actually does reduce to essentially this delta function, still without this condition n similar to x. Except that where we had that beta is compactly supported, right? On what? On big N, blah blah blah, where x1 is less than n is like so. Actually, it's still kind of the same. So it does make some sort of sense because n is bounded between x1 and 2 at x, where x1 is kind of like x to the 3/8. So if you have that bound and you have this bound, so implicitly there's kind of a bound on n here. I don't know if it's quite the same as n similar to x, because this is like squared, so this might be like n similar to square root of x, but at the very least this looks extremely similar to this delta function, and so this makes sense for why he's looking at this, to be able to bound delta, which is the point of theorem. Okay, I don't know if he's actually going to prove this, or if he's going to prove it later, or he's just stating this as something that's like well known in the field. Yeah, I'm not quite sure. I think this is actually part of assumption 2, supported on this. Okay, this is part of the assumption A2, where he's assuming that this holds, and so this looks very similar to what you would need to actually like complete this proof. So he's making quite a big assumption here. I don't know how he's... Okay, so probably there's going to be like a bit of work in proving, like choosing this like right beta and actually proving that it satisfies this like Siegel-Wolf's assumption. Because this looks like quite an involved thing to prove, and it's like basically looks halfway to the actual result. So this seems it might be difficult. And then okay, this is just conditions of J1 and J2 and this stuff. Okay, so this is like where the restrictions on n come from, because you restrict n over here, and then you don't have restrictions on m over here. But if you look at assumption theory, there are restrictions on how m and n like interplay with x. So yeah, this makes sense. So this is like 3 assumptions taken together that he's assuming about alpha and beta, where assuming these 3 assumptions, and then you take gamma to be the convolution, he's going to somehow prove that the this term is nicely behaved, and then somehow relate that to theta using some expressions of this form. Okay, so that makes sense. Cool. I don't quite understand exactly where these assumptions come from, but presumably they will be explained later. Okay, and then type 1 and type 2 estimates. We combine the dispersion method in 5 and 1, have these with the factorization 2.8 And 2.8 is that nice factorization of, really do need to organize this better. 2.8 is just where you get that nice d equals rq factorization with some freedom on r, and hasn't explained too much about that yet. Factorization here is close to n in logarithmic scale. I guess this is what he means by the freedom to choose r. Where it's like roughly on the same order of n. Okay. So he's going to like quantify this a bit better later. Due to the fact that modulo d is slightly greater than x to the 1/2. Okay. Why is this true? Oh, well, that's because of course the d is bounded by d squared, and then d squared is like x to the 1/2 plus 2 var pi, where var pi is like the 1/1.68. So yeah, this is just kind of by assumption. Okay, cool. After reducing the problem, estimating certain incomplete something sums. Actually, this is interesting because of this clues demand. I think there was an interview with Zhang where he was talking with Goldstone, I believe, and he was talking about how like people call this Clustomania, where like they were looking at these Clusterman sums, but apparently no one else had looked at modifying the main term, or like modifying the like lambda that was used, and also was working in this field of like Clusterman sums or Clustermania or whatever. And so Zhang was kind of in a position where he just happened to have both, and this is exactly what you need to make this breakthrough. So these two camps kind of didn't talk to each other, and I think Goldstone talked about how he never like learned much about these sums, but I guess he's going to have to now because this paper was published. Okay, we need only save small power of x from the trivial estimates. Okay. Blah, blah, blah. Okay, so I guess what he's saying is that because the modulo d is not too much above x to the 1/2, you can essentially just make a bunch of trivial estimates and then they save a small power. So the small power is going to be related to the small power that's above x to the 1/2. So what he's saying, I guess, this isn't going to be too difficult because he has a very nice bound on the modulus d. And I don't know much beyond that. I guess I'll see you later. Going to a Weil's bound for Clusterman sums. We'll fulfill it. Okay, sure. So this is not too difficult, is what he's saying. And there's existing work on this and just small modification. Here the condition, and go to the next one, which may be slightly relaxed, is essential. Okay, so this condition apparently is important. And let's go to the next one. I do get the feeling that perhaps there's quite a bit of background that he's assuming here, and like previous work and all that, that I should really read through first, but I'll see how far I can get without that. And even then, I'll probably just make some videos about the background. Condition, which may be slightly direct, is essential. So he makes this assumption here. X is supported on n, where n is greater than x1 and less than like 2 root x. And so the condition n is greater than x1, where x1 is like roughly x to the 3/8. x1 is roughly x to the 3/8. Is essential. So if this n is too small, apparently then bad things happened, and then you can't prove stuff about beta that you would need otherwise, even with this assumption, I guess. So, okay. Type 1 and type 2 estimates. I have no idea. Oh, here's where they define type 1. I overlooked this actually. We see the gamma is type 1 if this is true, and it's of type 2 if this is true. Okay, so of course you have n between x1 and 2 root x, but it looks like based on which side of x2 this is on, so if x is between x1 and x2, we see this is type 1, and if it's between x2 and 2 root x, then it's type 2. Yeah, sure. And so I guess he's going to have to do 2 separate proofs or something for these 2 regions. So I guess that's why he singles them out. And for these estimates, he combines, okay, this is where he's talking about how it's not too difficult. It's just a modification of some previous stuff. Okay, we say that gamma is of type 3 if it is of the form this. Okay, this is an entirely distinct form from what he was talking about before. If it is this form convolution of a bunch of stuff with, so alpha is still the same as before with absolutely different bound on that, on the divisor exponent. And such following hold. Okay, sure, some blah 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 conditions. Okay. This type 3 estimate relies on Birch-Bombieri result in Appendix 2.6, okay, which is employed by Freelander, blah blah blah, to study the distribution of the divisor cubed function, arithmetic regressions. Okay, so he's outlining how he's going to go about this. Okay, sure. This uses this result which Bombieri result is essential for type 3. Okay, result blah blah blah. Riemann hypothesis over finite fields. Yeah, so Riemann hypothesis in some sense has already been proved for finite fields. For some reason it's easier. I don't quite understand why that's the case, but apparently there's some tricks there that can't apply in the real case, the complex case. We'll estimate each blah 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 directly. Okay. One implies the method in reference 6 alone. Efficient estimates will be valid only for this. Okay, so apparently if you apply just the existing methods, you can get the correct estimate, but only assuming this additional assumption, which I guess he doesn't want to assume, where like m and 1. So here he only assumes that m and n1 is less than or equal to x1, where x1 is extra 3's plus 8 times like var price, this small factor. But you can only get it using previous results, extra 3/8 minus 5 halves of this and whatever. So he gets like just ekes out a little bit of extra exponent here, but apparently that's critical for what he's doing. But I guess the previous methods kind of get you most of the way there. Maybe not conceptually, but like in terms of like parameter space. Argument is carried out, blah, 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 with factorization. So he does reuse this argument, but he manages to like kind of push up this bound just enough to prove the result using this nice factorization d equals rq, where r is relatively small, and I think he also said r is close to n in logarithmic scale, so I guess this is what he means by relatively small. And this will allow us to save a factor of r to the 1/2. Okay. I don't know where he means save. Does he mean save here, and that's where he gets this extra bit of like power here? I'm not quite sure. We will see. Presentation, all of the alpha, beta are real numbers. Okay, sure, whatever. Okay, then we get into the lambda section. We're already at 40 minutes, so I think this is probably a good place to stop now. Got a bit less done today than yesterday, but I'll give a brief recap. So, let me organize these notes again. 1025, okay, 1024. Okay, so brief summary. We left off last time trying to figure out how to prove that this thing is positive, because this will give us the result that we want. We can break it down into, assuming this choice of lambda, we can break it down into 3 terms. One is the main term, this is a linear term with some coefficient, and then there's 2 smaller terms. So you want to do 2 things. One, make sure this coefficient is positive, and at least like L to the k0 plus 2L0, so that it's bigger than this term, and this term can't ruin your day by being like big and negative. And then you also want to show that this error term is small relative to the main term. And then for sufficiently large x, this will immediately give you that this is positive. Okay, good. And then it turns out that you really can't do this using the existing choices of lambda. I think this is the GBY sieve, I should check that. You can either get one or the other, but not both. But it turns out that if you make this small modification where you add the additional constraint within the definition of lambda, so the sum has 2 constraints here, and you add the additional constraint that it divides like this kind of curly p where it's a product of distinct primes, then it turns out that you can still prove that this bound on the main term still holds. It's still sufficiently nice and like goes fast enough, but you are able to actually provide a bound for the error term that's like nice enough and is unconditional. So that's the approach he's going to take here. And how he abounds this error term, it turns out that the reason why it adds this additional assumption is that d is like then nicely factorable because it's a product of distinct primes, and you kind of have some control over what these primes are, so you can have some control over the factorization, and this will be quite useful for bounding this error term. Okay, yep, and then he like makes some explicit choices, which I'm assuming he just did after going through the whole paper once and then like actually figuring out what this needs to be. He defines some auxiliary functions, so you can like define all the stuff more nicely. You can write the original choice of lambda in this way, and all he did was just add an additional assumption where d divides this curly p. And then this will kind of give him the new stuff. And then he just defines a bunch of auxiliary things. I think this is all like blah 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 technical stuff. And then here's where he actually starts proving results. So this is similar to a part of the error term that he derived, and he's going to bound this, and so this will like presumably help him bound the rest of the error term. And here he just goes into a digression about how he's going to do this. So he wants to look at this term individually, which makes sense. And first he's going to prove some result where instead of theta you have a Dirichlet convolution with specific forms on specific conditions. Here's more specific conditions about stuff. And then he's basically going to go into more detail about how he's actually going to prove this theorem 2, where he splits this into several cases, like this type 1 and type 2 estimates, and this like type 3 estimates. And for each of these, he's going to outline like which previous results he's going to use and like what slight modifications he's going to do. And so starting next time, we'll go into this section full of lemmas, where he's presumably going to outline some stuff that will actually be used in this proof, so we have a good, deeper understanding of where he's going to go with this theorem 2 and like exactly what results, like what his approach is to be able to bound this error term. I'm still not sure how he realized how to make this change, probably just like after a bunch of trial and error, and I don't think he's actually going to say in this paper how he came up with it, but it's at least good to understand like why this works and how he's going to show that it works at all. Okay, so I guess that's enough for today. If you're watching at all, thanks for watching as usual, and yeah.